In this video, we will be going over first order ordinary differential equations and the first method to solve them, integrating factors. So to start off, first order linear ODEs are typically in the form a of t plus b of t. Sorry, a of t y prime plus b of t y is equal to c of t. Now this equation isn't in the standard form, but it just shows us that every term has a coefficient. Now how do I know this is first order? Well, the y prime and the y tell me that this is first order. If I had something like y double prime plus whatever, y prime plus whatever, y is equal to whatever, this is second order. And it keeps going on and on and on. You can have even higher order equations. But to keep things simple for now, let's focus on first order. So I have a y prime and a y. That tells me this is first order. But now, typically in differential equations, we can rewrite this equation into what's called the standard form. So to do this, we divide by the term next to the y prime. So like I'll divide by a of t. This leaves me with y prime plus b of t over a of t times y is equal to c of t over a of t. This is the standard form, but so this is standard form, but we can rewrite this. We can make it even simpler. We can rewrite this term and this term. This becomes p of t times y, and this will become, we can call it g of t. Most textbooks call it g of t. Okay, now that we have this in standard form, we can talk about integrating factors. So when you're given an equation like this in standard form, or even like this, you might have to make it standard form, we can use what's called integrating factors. Integrating factor is defined as mu is equal to mu of t. This is our integrating factor. So here, let me write this. Integrating factor and this is where mu is equal to e to the integral of p of t dt. And yes, this is the same p of t as up here. This comes from this. We take the p of t from our standard form and we plug it into this formula here to solve for our integrating factor. Now let's look at an example. So this example is t y prime plus 2y is equal to 4t squared. Now you'll notice this is our a of t. This is our b of t. Oops. B of t. This is our c of t. It's not in standard form because we have a coefficient on top of here, right? We don't want this. So we're going to divide by t, and then we get y prime plus 2 over t times y is equal to 4t. Okay, now that we have this equation written in standard form, we know that this is p of t and this is g of t, right? So now, to solve this equation here that we have here, we can use integrating factors. So we know that mu is equal to e to the integral p of t dt. So now we plug in for p of t, e to the integral 2 over t dt. Okay, so if we integrate this, we have e to the natural log, 2 times the natural log, absolute value t, plus our constant of integration. Right, we all learned this in previous calc classes. So now what I'm going to do, let me add another page to this. Okay, so now what I'm going to do is rewrite this. So we'll be left with, remember, anything times the natural log can be rewritten like this. Since this was multiplied by 2, we can take the exponentiate the inside of our natural log to whatever was multiplied out front. So it becomes ln t squared. It's one of the log rules. And we still have that plus c. So now we can rewrite this as e to the ln absolute value t squared times e to the c. This becomes any time there's a natural log exponentiated, we can just rewrite it as this. So we have t squared times e to the c. Now we can rewrite e to the c as a new constant k times t squared. Now for integrating factors, for first order linear ordinary differential equations in general, the constant here has to be non-zero. So it could be any non-zero, so we can call it 1. So now this tells us that our integrating factor is t squared. Now, for integrating factors, there's a long, convoluted process to solve them, but there's also a shortcut. So this shortcut tells us that we can multiply mu by y and set it equal to the integral of g of t from our standard form, so 4t. So we'll have gt times, let me write this in green. So we have mu times y is equal to the integral of g of t times mu dt. So plugging everything in, we are left with t squared times y is equal to the integral, our g of t 4t times mu, which was t squared, so t cubed, dt. We're almost done. All that's left to do now is integrate the right side. T squared y equals, if we integrate this, that becomes 4t to the 4th over 4 plus a constant. Those 4's cancel. We're left with t squared y is equal to t to the 4th plus c. We divide both sides by t squared. Y is equal to t squared plus c over t squared. This is the solution to the differential equation that we were given. This is a non-initial value problem though. I would like to look at one initial value problem. So let's come down here. Here's example 2. Okay. Oh, wait a minute. I forgot the initial condition. Let me see. Okay, so we're given y of pi is equal to 0. So if you look back, hold on, let me fix this order here. Let me move this down. If you look at this answer to this question, we're left with a constant on the right side. So basically what an initial condition does, this right here, it allows us to solve for the constant that we will get. It's called an initial value problem, with this being our initial condition. That's our initial condition. So we're going to solve this differential equation the same way we solved the last one. Now, if you look at it, it's already in the standard form, right? This is our P of t. So our P of t, let me just write it down here. Our P of t is 2 over t. And our G of t is equal to cosine t over t squared. So let's solve for our integrating factor. We have mu equals e to the integral pt dt, e to the integral 2 over t. Oh, this is the same thing as the last problem almost. That's the same P of t. So that makes our life a lot easier. We know that this is e to the 2 ln absolute value t plus c. Since we already solved this, we know that mu is equal to t squared, right? Same thing as the last problem. Same exact thing. So now that we have mu, remember we have mu times y is equal to the integral g of t times mu. You plug mu in, t squared y is equal to the integral. Our g of t this time, a little more complex. We have cosine of t over t squared times t squared. Oh, the t squares will cancel. Perfect. Makes our life a lot easier. So now t squared y is equal to, cancel these out, integral cosine of t. This becomes t squared y is equal to the integral we already did that. So the integral of cosine is sine of t plus c. We can now divide everything by t squared. So y is equal to sine of t over t squared plus c over t squared. Now this is our solution to our differential equation, but it's not the solution to our initial value problem. We're asked to find the solution to the initial value problem. So we're given an initial condition, y of pi is equal to 0. This basically says we have a y as a function of t is equal to something, right? So our t value is pi, and our y value is 0. Is what this initial condition says. So now, let's combine let's combine the solution to our differential equation. So we have 0 is equal to sine of t over, oh, wait a minute, t is pi, sorry, over pi squared plus c over pi squared. Now, sine of pi is 0, so we're left with 0 is equal to c over pi squared. This tells us that c is equal to 0. So now the solution to the IVP is sine of t over t squared plus 0. Now if you notice here, I had this other example problem. I'm going to give you guys the solution to this question. So the solution is, let me find it. The solution to this question is y equals t over 3 minus 1/9 plus 1 over e 2t plus c over e to the 3t. You see, it's not an initial value problem. You just want to find the general solution. You gotta find the general solution. So I want you to pause this video and find the general solution and see if you get this answer. Okay, now that you should have this answer, if you couldn't figure it out, I'm going to do it for you. So, you see it's already in standard form. Let me box this off. So it's already in standard form. Oops, our P of t is equal to 3. Our G of t is equal to t plus e to the minus 2t. Mu would be e to the integral of 3 dt. That's e to the 3t plus c. That's equal to k e to the 3t. K is 1. So that tells us our integrating factor is equal to e to the 3t. Fantastic. Now we use our little trick. Mu times y, so e to the 3t times y is equal to the integral, our g of t, times mu, so that's e to the 3t times t, plus mu times e to the minus 2t. We can add the exponents together. That's e to the 3t minus 2t, e to the t. So, unfortunately, if you notice, we have a product here. We have to do integration by parts. So, I'll pick my u to be t, because I'm going by LIPET. Oops, I forgot the I. LIPET, LIPET. So we have E. Okay, wait. I'm getting ahead of myself. So my U would be polynomial. We have t first. Du is dt. My dv would be e to the 3t. My v would be 1/3 e to the 3t. Now, e to the 3t times y is equal to the integral, u dv. Remember, it's uv minus integral v du. So we have t times 1/3. So we have t over 3 times e to the 3t minus the integral. I'm going to pull the 1/3 out from the v. So we have minus 1/3 integral the rest of the v, e to the 3t, times du, which is equal to dt. And then don't forget, we also have this integral of e to the 3t. So now we have e to the 3t times y is equal to t over 3 e to the 3t minus 1/3 times 1/3 e to the 3t plus e to the t. Right? Because the integral of this is just e to the t. This becomes e to the 3t times y is equal to t over 3 e to the 3t minus 1/9 e to the 3t plus e to the t. It's a lot of e's. Now, we can divide by e to the 3t, so this will cancel with this. Unfortunately, we still have this over here, so we have y is equal to t over 3 minus 1/9. Wait, am I missing a term? Oh, wait a minute. I forgot my plus c. Oh, geez. So up here we have a plus c, don't forget. After these integrals, well, technically, actually, we have, if we integrate this one, we have plus c1. Then if we integrate this one, we have plus c2. So that'll make a new constant. We'll call it c. So c1 plus c2 is equal to c. We'll call it c. Sorry about that. Minus 1/9 plus e to the t over e to the 3t plus c over e to the 3t. Y is then equal to t over 3 minus 1/9 plus e to the t. So that's e to the t minus, so this will just become either e to the minus 2t, or you can write it as 1 over e to the 2t plus c over e to the 3t. And that's our solution to this problem, which should be what's up here, right? Yep.